In this video, I want to talk about the cross product. First, I want to describe what the cross product is, and at the very end of the video, we'll see a calculation formula for the cross product. Imagine that you have two vectors, u and v. So maybe we have two space vectors, u and v, right? And they don't have to be the same length, but I just have two vectors in space. One of the nice things is after I have two vectors, I know they lie in a plane together, right? I can use those two vectors to kind of determine a plane, so that's going to let me draw a picture on my board, even though what I'm talking about is certainly true for space vectors. So let's consider two vectors, v and u. Okay, so I have vectors v and u lying in a plane together. Right, so right now, this says imagine any two vectors. I'm certainly imagining two vectors right now that are not the zero vector, right, because they have length. And I'm also imagining two vectors right now that aren't parallel. They don't have the same direction. So I might not have really followed through on the imagine any two vectors yet, but right now we'll just let this u and this v kind of hold the place of any two vectors. It is worth noting they're definitely not the zero vector and they're not parallel. They don't share the same direction. All right, let's think about a unit vector n. Let little n be a unit vector that is perpendicular to both u and v following a right-hand rule. From u to v. So if I look at my two vectors, I'm defining a unit vector n. It needs to be perpendicular to both vectors. So if I had vectors v and u that look like this, I could have a vector perpendicular to both that kind of pointed out this way, and then another one that pointed out this way, and then the next part tells me which one I'm talking about. Then it follows a right-hand rule from u to v. So if I think about these two vectors on the board, my little n either points straight up towards the camera or points below the board and into the countertop. But since I have to follow a right-hand rule from u to v, little n is a unit vector that points straight out of the board. So something like that. Imagining that marker length to be 1 unit, right? Coming straight up out of the board towards the camera. The cross product of u and v is the vector with direction in and magnitude that is the magnitude of u times the magnitude of v times sine of the angle between u and v. So the cross product, u cross v, and this is how we denote the cross product. We literally write u cross v, is the vector with magnitude. And of course, we can always write down a vector as a product of its magnitude and its direction. Okay, so I calculate this magnitude, I multiply n by it, and I get some vector that I call u cross v. Now, let's think about that magnitude for a minute. So I have two vectors, u and v. Angle between them. And if I construct a parallelogram, like I was thinking about the parallelogram law from before, If I want to calculate the area of that parallelogram, I'd have to remember that the area is a base times its height when I'm talking about a parallelogram. So I'd need to know the height. Well, looking at this little right triangle I just formed, sine of that angle is equal to that height over the magnitude of V. So when I go to find the area of that parallelogram, the base has a magnitude of U, and then the height has this length. And there's that calculation from before for the magnitude of the length, or the magnitude of the cross product. Okay, so U cross V has a length that is the area of the parallelogram spanned by both U and V, and a direction that is a unit vector perpendicular to both U and V. So I understand the cross product in terms of its magnitude and its direction. The two most important things about any vector, I can always write down a vector in terms of its length and its direction, but this isn't probably the best calculation formula, right? Because nothing in this definition of cross product helps me calculate it. So, if I have two vectors, U, which is U1, U2, and U3, and V, that is V1, V2, and V3, it would be nice to have a formula to calculate the cross product. And this is that formula. Some of you might have even seen this in a physics class when you talked about torque, because later on we'll actually use the cross product to calculate torque. And you might have seen that formula look something like this. All right, and there's a calculation formula for the cross product. That given two vectors U and V, and each of their components, I can calculate the components of my cross product vector. Your textbook includes a derivation of this formula using this definition and then several properties of the cross product. What I would like to do in the next few videos is show you a different way of thinking about this calculation formula using determinants. And a determinant is a property of a matrix. So I want to teach you about matrices and determinants to kind of understand this calculation formula better. Then I want to use the determinant to rethink this calculation, to redefine the cross product. After we've done that, I want to show that this calculation formula actually matches this definition in all the important ways.